So let's start with the introduction. My name is Ankit. I work in NTT Communication as a research engineer. My research mainly deals with high performance computing and GPU related technologies.
I'm Takeaki. I'm working for NTT Communications as a research engineer and OpenStack operator.
So before we actually start our talk, I would like to mention you that we also had a talk in OpenPOWER Summit at Las Vegas this year. In that talk, we mainly focus on how to enable KVM in POWER system. So if you are interested to know more about how to enable KVM in POWER and some interesting benchmarking results, so you can go through this link, this one. So let's start with the agenda. In the background, we will discuss about mainly our GPU cloud and our motivation to use POWER system, our OpenStack environment. Next, we will talk about our goal and our approach to deal with our goal. And then we will conclude with the conclusion. And at last, which is not in the list, we will talk about our other choices like Kubernetes. So let's start with the background. I hope many of you knows about NTT Communications. It is the largest telecom company in Japan. NTT has like subsidiaries and offices more than 100 cities all over the world. And it is also the part of Fortune Global 100 company. Talking about our work, we provide our GPU private cloud and provide the GPU instance to our in-house users to do like their work on the run some deep learning algorithms, do some HPC applications. For example, we have the AI communication engine called Kotoha, which analyze the written and spoken language with very high precision. And it also has many other applications. So if you want to know more about Kotoha, you can just go through this link to just learn how it works and its architecture. We also do deep learning training on customer data, which is time series data, to just predict the quality of products and anomaly detection. So this is our work. This is our internal OpenStack environment. So as you can see here, we mainly provide NVIDIA's K10, M60, and P100 GPU card in x86 servers as a compute node. So our in-house users use the instance with these GPU cards for their applications. So this is our main motivation for using the IBM Power system. So as you can see the bottom left figure, this one, it is Intel-based system called DGX1. And this one is IBM Power system, which is also known as Minsky. Minsky is a code name for that. In Minsky, CPU and GPU are connected via NVLink. But in DGX1, CPU and GPU are connected via PCLE. So that's why the bandwidth is more in Minsky as compared to DGX1. Also, the bandwidth between CPU sockets is more in Minsky. And the bandwidth between CPU and memory is also better in Minsky as compared to DGX1. And that's the reason we have decided to integrate Power system to our OpenStack environment. So our goal is how can we further boost the performance of Power system. So we have the two approach for that. So first one is to tune up the performance of Power system as a bare metal server. So first we try to benchmark power rate system with the nbody. Nbody is a simple CUDA sample program. This is a sample command to run the benchmark. You can also mention your numbodies and your available devices. So our main focus to use nbody to just emulate the memory intensive workflow. So as you can see here, in nbody, the GPU threads read data from main memory and not from the GPU memory. So it frequently reads data from the main memory. So our main focus to know that how the bandwidth between GPU and CPU affects the performance. So after benchmarking, what we have found, when we specify two unlike GPUs, we got different performance for two GPUs. And for 4 GPUs, the result is not scaled very well. So what is the reason behind this unscaled result? So we investigate the reason behind that, and we found the solution. And the solution for this is memory interleave. So by the way, how many of you knows about memory interleave? Can you please raise your hand? Anyone? Cool. So what memory interleave does, it allows to use memory equally from available CPU sockets. So this is the command to execute memory interleave. And if you see the bottom figure, the bottom left, this one, it is a case when the memory interleave is disabled. So, and the right is when memory interleave is enabled. So when it is enabled, it uses memory equally from two available CPU sockets. So we will see it case by case in the next coming slides. So this is the case when memory interleave is disabled, and this is the default case. So these are the 4 GPUs, GPU0, GPU1, GPU2, and GPU3, which are connected to CPU via NVLink. In this case, GPU0 and GPU1 always read data from closed memory. So this GPU0 and GPU1 reads data from the closed memory, and GPU2 and GPU3 reads data from the far memory. So in that case, if we check the elapsed time for one iteration, what we have found that GPU0 and 1 has around 4.3 to 4.4 seconds, and for GPU2 and GPU3, we get around 9.2 to 9.10 seconds. So there is a difference of time. And the result we got around 8,500 GFLOPS per second. So when we enable the GPU, the memory interleave, what we have found, GPU0 and GPU1 reads half of the data from closed memory and half of the data from the far memory. And it is same for all remaining GPUs. So in this case, if we check the elapsed time, what we have found, all the GPUs has the same elapsed time, and which is 5.2 to 5.3 seconds. And the magic happens. We got the better performance than the previous one. So this is the final result after we enable the memory interleave. So what we have found, the graph is scaled very well as compared to the previous one. So here we have compared power rate with the DGX1 when memory interleave is enabled. So as you can see here, the power rate has scaled up very well as compared to DGX1. So what is the reason behind this? In the Intel-based architecture like DGX1, it has narrow I/O bandwidth, and in that case, memory interleave doesn't work very well. So that's the reason the DGX1 is not scaled very well. So our next approach is to integrate power rate to OpenStack environment. And from here on, I will hand over the talk to my fellow colleague.
Thank you, Ankit. From here, let's think about integrating OpenStack. First of all, we decided to integrate Power Server to existing Intel-based OpenStack cluster. Because we thought creating new Power 8 OpenStack cluster is too much. So controller and other compute Intel servers. Next, what is the requirements for OpenStack? Linux can run on Power 8, KVM can run on Power 8, OpenStack can run on Power 8, and the offshore package repository is also available. So basically, same procedure can be used as Intel servers. In addition, GPU nodes require KVM PCI pass-through feature. It needs KVM and IOMMU support. QEMU 2.6.1 or later supports Power GPU pass-through. And Power Server has IBM transition control entry as IOMMU. So enough. So our environment is like this. We use Power 8 server with NVIDIA P100 GPU. It is called Minsky. And Ubuntu Xenia, KVM 2.11, and Queen's Nova from Canonical Official Repository. Here's OS configuration. Only one unique point exists. When using KVM on Power servers, SMT cannot be used. SMT is simultaneous multi-threading. It's just like Intel hyper-threading. By default, Minsky has logical 160 cores, but in using KVM, we can use only physical 20 cores. Nova configuration is completely same as for Intel servers. Specify vendor ID and the product ID, set the alias, enable PCI pass-through filter. Now, Power 8 server is integrated to OpenStack. Next, how is the VM performance? Let's benchmark. This is the flavor of the VM for benchmarking. For memory performance, huge page is enabled. This is the nbody benchmark results. This graph left to right, 1 GPU, 2 GPU, 4 GPUs. Blue one is VM, red one is baremetal. The performance is drastically degraded when using multiple GPU. We tried to discover what is the reason of performance degrade, and they found cheap memory bandwidth between CPU and GPU. Left graph is host to device bandwidth. Right one is device to host. Both of them, Power 8 VM has 1/5 of Power 8 baremetal performance, and even half of Intel baremetal or VM. In this state, there is no reason to use Power 8. Why? Is this virtualization overhead? But Intel VM is not degraded. The reason is NVLink implementation. I don't know actual implementation, but Linux recognizes NVLink as like this. One NVLink connection is achieved with 2 NVIDIA NVLink devices and 1 GPU connection. If you use flavor with GPU device ID, of course, OpenStack attached only GPU device. And the Power 8 connects GPU with PCI Express by 8. This may be the reason it results half bandwidth of Intel servers. So pass-through 3 devices solve this issue. Let's try. First of all, we have many devices. Which device is connected to which GPU? GPU and the NVLink devices have lock code. You can see like this. For instance, if PCI address is 210.0, it is GPU 1. These are NVLink devices. Same procedure show lock code. If you use GPU 1, connected to NVLink devices are these two. We added NVLink devices to revert XML files like this, redefine domain, and relaunch the VM. How is the benchmark? With NVLink device VM, the performance is improved to almost same as baremetal. Nbody benchmark with multi-GPU is also improved. And of course, it is better results than Intel servers. Next, how can we manage NVLink devices? NVLink devices are also PCI device. It seems to work to use OpenStack PCI pass-through function, same as GPU. But OpenStack does not know which device is connected which GPU. So if you request one GPU and two NVLink devices, wrong device may be attached. In ideal, we think the group of PCI device can be defined, and when request device set, multiple devices are set in the same time. But currently, we cannot do like this with OpenStack. Our current solution is like this. As a simple script between libvirt and QEMU. In OpenStack world, simply request only GPU, and the script find which GPU is attached and add related NVLink devices automatically. As a result, we can get the VM with GPU and the correct NVLink devices. Okay, conclusion. Yes, we could boost the performance with Power Server with several points you should know. Memory interleave, adding compute node, and pass through not only GPU but also NVLink device. Power 8 has powerful CPU-GPU connection faster than Intel servers. In system memory interleave case, we can get better performance. In OpenStack integration, there are some limitations. When using KVM, SMT cannot be used, and the OpenStack doesn't support NVLink device. Okay, extra contents, another choice. How is the container? How to manage container and GPUs? So Kubernetes. Kubernetes is container orchestrator. It has container scheduler including GPUs. To schedule GPUs, its device plugin feature, NVLink device plugin, and the NVIDIA Docker are required. Kubernetes device plugin feature is alpha until version 1.9. You have to enable this feature like this, but now it is beta, so the feature is enabled by default. At first, about NVIDIA device plugin. NVIDIA device plugin manages GPUs with Kubernetes. Official Docker repository includes only Intel image. We have to build for power architecture, but it is easy, like this. Next, NVIDIA Docker. NVIDIA Docker is the runtime can manage NVIDIA device and the NVIDIA drivers with Docker. Recently, official package for Power architecture became available. You can install using apt-get install. Finally, we have to change the default runtime to NVIDIA and enable NVIDIA device plugin. Okay, now you can see GPU resources from Kubernetes like this. And you can see you can use GPU from Kubernetes correctly. And the NVIDIA Docker supports NVLink. So without any tricks, we can use full bandwidth. You can also use container on baremetal or also container on VM with NVLink. That's all. Thank you for listening.
Thank you. Any questions?
So unless other folks are going to come up to the microphones, I'm going to totally hog this so other people have questions. I'm curious how you got PCI pass-through to recognize the GPUs on using Nova. Did you have to hack Nova code to do that? Or did you just set it up and it worked?
Just to enable the PCI pass-through. PCI pass-through. So like, did we change any Nova configuration or something?
So, we did not modify Nova code, and just.
So it just worked. When you put it into the PCI pass-through whitelist and you kicked off the VM, it just attached the GPU to the VM?
Yes.
Were you using the Nova Power VM out of tree driver?
No, it's not Power VM, it's KVM.
Oh, I've been misconception this whole
Yes, KVM.
Actually, we had to first check how to enable the KVM in the Power 8.
Okay.
So like in our previous talk, as I mentioned, we had a talk like how to enable the KVM in the OpenPOWER Summit. So like if you're interested, like how to enable KVM in Power 8, you can just check that. And after enabling, we just did some verification, and after it enabled, we did pass through on GPU.
Okay. Yeah, that was what I was confused about, because I write the
Yes,
I write the code that would make this work on Power
actually,
VM.
I haven't mentioned that the KVM configuration in the slides.
Okay.
Yeah.
Okay. Was there? Yeah.
What OpenStack distribution are y'all using?
Pardon?
What OpenStack distribution are you using? Are you just pulling things down from upstream, or are you using like Red Hat or Ubuntu? Or
Ubuntu.
We are using the Ubuntu right now.
Say again?
We are using Ubuntu right now.
Ubuntu's?
Yeah.
OpenStack, okay. I think there's also some work that's going into Nova upstream in Rocky and going forward that will allow you to fix the problem that you were talking about, where the NVIDIA is really 3 devices, and you need to make sure that the right 3 get attached all together.
Okay.
That's a problem that should get fixed.
Okay.
But I don't know if it'll be in Rocky or if it'll be beyond that. He would know better about that.
Thank you so much for your comment.
Thanks, guys. There's been some efforts to try to get the PCI bus or topology pass-through for multi-GPUs. I don't know how that works with NVLink, but I'm interested to know if you are aware of any ability to do GPU direct, so peer-to-peer transfers between virtualized pass-through GPUs.
Actually, we haven't tried the direct GPU connection, so maybe we should try the direct connection of GPU. But like before, we had to enable the KVM, and after that, if it like first we did verification, like it is work or not. So like in our case, we just tried that. But as you said, like the direct GPU connection, we haven't tried it yet. Thank you.
Well, what I'm interested in is if there is any possibility to deploy Linux with OpenStack via directly as using the Power VM feature, not the Power KVM and even not Power VC, simple Power VM with OpenStack. Is it possible? Do you know?
Actually, it's a PCCLE architecture in IBM Power systems. So maybe we have to use Power VM or Power KVM in that case.
So we have to use Power VC or Power KVM. Or is it also possible to use
Power
VM?
KVM, yes.
Power KVM, but
Yes.
it's not possible to use Power VM directly from OpenStack.
Actually, I'm not sure like IBM supports that, but like IBM has mentioned that like, they support Power KVM, so we use that.
Okay.
Yeah, so I can actually answer this question because that's what I do
please.
for a living, is get this to work on Power VM. So there will be a way, hopefully within the next release or two, for you to use Power VM natively in Nova, or possibly with the out-of-tree Nova Power VM driver. You won't need Power VC, but you could use it. That would allow you to do all of this that they've talked about without having to hack code, which is what you'd have to do today.
Okay.
Yeah.
Sounds great. So we should.
Yeah, we should talk. Let's talk after this. Thank you.
Thank you so much.
Thank you.
Thank you. Any other questions?
Thanks for presenting. Have you tried on the Ironic on the whole power system? Ironic. Have you tried Ironic?
Amnik? No.
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 We haven't.
Okay.
Okay, guys, thank you so much for joining. We have one more question. Sorry? Grid? Grid drivers?
Grid drivers not supported. Answering it only on the x86 on the ladder.
Okay, he answered your question. Okay. Thank you so much for joining us.